Hello and welcome to lesson 27, our very first lesson of our curve sketching unit, and this is unit 4 now. So again, you've seen a lot of derivatives, you work with derivatives, you know what they are as a rate of change, you've done derivative rules, you've seen optimization problems, and we're now working with our last application of derivatives, which is for curve sketching. So we're going to be practicing drawing a series of polynomials, rational polynomials, and as well as some of our special functions using a method, which is a curve sketching method. And to do that, we need to analyze certain characteristics of these graphs and functions. And our very first one is critical points. And you've actually heard me use critical points in the previous unit, especially when we were talking in optimization. And so we're going to now give it an actual definition and generalize this to any given function. So not necessarily in optimization problems, but for any given function, what the critical points are. So our learning goal today is to determine critical points by applying the first derivative test and solving where the first derivative is 0 or undefined and using this to determine extreme values. And this is also now a repeat concept. You've seen the algorithm to find the local extrema, and that's exactly what that is, the extreme values. So before we get into that, let's build some background knowledge. So we know that a function can be increasing or decreasing. So when it's increasing, it means that, and it can be on a given interval. It's not, we don't necessarily have to have that the function is increasing for all values, but for a given interval, it could be increasing on that interval. And when it's increasing, it means that when x1 is less than x2, then the output f of x1 is also less than f of x2. So for example, we are going like this, then we see that this is x1, and then f of x1, and this one is x2, f of x2, and clearly it is more. And similarly, for decreasing, we might have something like this, where as x is increasing, so this would be x1 and x2, then the output is now, the output of the first one is greater than the output of the second one, or the output of the second one is less, so we have a decreasing function. So now let's practice with some functions we should be very familiar with, our linear equations as well as our quadratic function. So what are the intervals of increase or decrease for these given functions? So starting with f of x is equal to x, we know that this is a straight line such as this. And so for any two values of x1 and x2 that we pick, then we have that this is actually an increasing function altogether because all the outputs are greater than the output of previous x values. Now similarly, f of x is equal to negative x, we have such a shape. It's a straight line like this. And so for any x1 and x2, again, we have that the outputs are decreasing. And I am just extending or putting my arrows there to show that these lines are extending because I haven't told you what interval this is. Because for these two functions, it actually works for any interval that you look at. Now our parent function for the quadratic, f of x is equal to x squared, which looks like this on our, so we have x and y, and then maybe let me just draw this with a different color. This is x squared. And so for this one, let's actually work on it together. So considering the function f of x is equal to x squared, and its derivative now using power rule is 2x, then when x is less than 0, the tangents, which are given by this value, are all negative. And so the function is decreasing. And we can actually see that just from this curve that I've drawn here. All of these values, they're decreasing. And then similarly for these values, we have increasing. So the outputs of any x2 I choose here and x1 I choose here, the output is greater. So then when x is greater than 0, the slope of the tangents are all positive, and the function is increasing. And yes, again, exactly here we have our function and we can see this part is decreasing. So here we have decreasing. And here we have increasing. And so now you might be thinking, what happens at x is equal to 0? Because this is x is greater than x is greater than 0 and x is less than 0. But what happens at x is equal to 0? So at x is equal to 0, the function changes from decreasing to increasing, and the slope of the tangent is 0. And so this point is called the turning point. And if you remember our optimization problems, this is the change of direction. So if we are going decreasing till this point, and then now we change direction and we are increasing. And our instantaneous rate of change, which is the slope of our tangent here, is also, it's a horizontal line, so it'll be equal to 0 here. And so now we are seeing what those critical points that I was referring to refers to now in this context. So a turning point specifically is a point on a curve where the gradient changes from increasing to decreasing. And it could be a maximum or a minimum. So for example, if we have negative x squared, we also have this point, which is our vertex. This is also a turning point. Now we are just going from increasing, we change direction, and now we're decreasing. And now generalizing this a little bit more, we have critical points. So a point C, f of C, of a function f of x is considered to be a critical point if f prime of C is equal to 0, and we saw this again with optimization problems, or when it is undefined. And this one we maybe haven't seen a lot of, but we're going to see in our next lessons, as well as in this lesson. And these points are candidates for local extrema, so those maximum or minimums. And consider again, these are local, so given a specific interval. And these may also be called saddle points. So consider like a saddle, this is the top of the point, or if we are going the other way, this is our minimum. Oh, our minimum here. And so these are turning points, critical points, or saddle points. But you'll often hear critical point moving forward from here. And again, local extrema could be a local maxima or a local minima. So a local maxima is the highest point of a function within a specified interval of its domain. So again, on a given domain, on a given interval, what that maximum could be. And we saw that it could be either at the endpoints or at these critical points. So that point is considered to be a maximum if at f of a, this output is greater than all the other outputs f of x on that interval. So also as we are getting closer and closer to, so for example here, this would be a f of a. So as x is approaching a from either side, we see that all these values are less than, or all these output values are less than f of a. So that makes it a local maxima. And similarly, a local minima, we have that it is, the output is less than all the other points. And again, as x is approaching a, here, we find that the output of A, so f of A, is less than all the other outputs. And this is actually giving now our first derivative test. So let f prime of C be equal to 0, so a critical point. And if f prime of x changes from negative to positive at x is equal to c, so the tangents are going from negative, so as you can see, this is a negative tangent and it's becoming positive now, then we say that this is a minimum or a local minimum. And if f prime of x is now, so the tangents, slope of the tangents are increasing, they're positive, and then they suddenly become negative, at the point that which we have f prime of c is equal to 0, then we say that this is a local maximum, and we can clearly see from the graph here as well. So if ever you're not sure, consider those slopes of the tangents and try to visualize, especially with just a simple quadratic for yourself. Now, f prime of c is equal to 0 may also imply something other than a maximum or a minimum. So, for example, consider y equals x cubed. So, if you remember from uh, functions, x cubed has script with different colors. So, x cubed has a graph that looks like this. So, this isn't necessarily a maximum or a minimum, depending on the interval you look at, especially if I consider an interval perhaps -1 and 1, then this is not a maximum or minimum. In fact, our endpoints here are actually going to be the minimum and maximum here. But this is still a turning point for us because our curve has a point in which the instantaneous rate of change is briefly equal to 0. And that's exactly what happens here. Now, consider for this given function, we want to know what values of x is the function increasing or decreasing. So this is a cubic function now. We're going to see what this would look like. So first we're going to determine the critical or the candidates for the local extrema by solving for x when dy by dx is equal to 0, so our derivative. And this is y prime is equal to, and this is now just my derivative rule, so I get 3x squared plus 6x, and this -2 is just a constant, so it's not contributing to our derivative. And now factoring this, I have 3x and x plus 2, so this is equal to 0 when x is equal to 0 or when x is -2. So now we have two candidates for our local extrema, and we want to find out if it's a maximum or a minimum, and based on that, we're going to determine the intervals of increase or decrease. And so I set this table up for you, and I suggest you take a moment and try to fill this on your own. So for the sign of the derivative, you can always just pick any point within these intervals. So what I've pretty much done is take these points, x is equal to 0 and x is equal to -2, and I've split up my function into the different intervals based on those candidates for my local extrema or based on my critical points. So now here I might choose, for example, x is -3. Here I would choose, hold on, x is -3 here. Here I might choose x is -1, and then here I might just choose x is equal to 1. And so you should see that the derivative here is less than 0, and the derivative here is greater than 0. And so the slope of the tangent here is negative on this interval, and this one it is positive. And so based on this, we can conclude that here we have a decreasing interval, and here we have an increasing interval. And so that's actually what the first derivative test also tells us. When the tangents are negative, then we have decreasing function, and when they're positive, we have an increasing function. And so how does this now relate to the graph of the cubic function that we started with? So consider this, the curve here. So this is our y function, and the red lines are just showing you those critical points. So here we have the two critical points. And as you can see, any tangent I draw here, these are positive tangents. And we can clearly see our function is increasing here. And then we have a turning point here, so a change in direction. And now the slope of the tangents here something like this. It's hard to draw because it's getting really close, or like the points are close together, but a rough estimate like that. Okay, let's call it a day. Okay, then we have decreasing tangents here. And so again, we can clearly see the function is decreasing here because all these outputs, as x is increasing, the outputs are getting smaller and smaller. And then we have another turning point at x is equal to 0, and we can see that these slopes that are now positive again, and our function is increasing for this interval, and it will continue to do so as x approaches infinity. And same with here, as x approaches negative infinity, we still have an increasing interval. And that's why we have x is less than 2 and x is greater than 0 as our intervals there. And one last thing you should add here when solving these problems is just writing your answer as a concluding sentence. So the function is increasing when x is less than 2 and x is greater than 0, and the function is decreasing when x is between -2 and 0. And these are exclusive intervals because x is -2 and x is equal to 0 are the critical points, so they're not actually increasing or decreasing, they're just critical points. Now, let's look at extreme values and our absolute extrema. So, the maximum and minimum values of a function over its domain or a given interval are known as the extreme values or absolute extrema. So, for this example here, what is the highest point? And this actually occurs right over here. And this would be, and this let's say is 1, 2, and this is -1, -2, and this is 1, 1, 2, and then -1. So it's a 1-to-1 scale. So then this point over here is -1, 1. And that is the highest point on our curve. And this one gets really close, but it's clear to see this one is even higher. The output is higher. So this is our highest point, -1, 1. And that's why it was important for all those optimization problems and for our algorithm to check those endpoints because sometimes they are the maximum or minimum values and not the critical points. Now, this is called our maximum at -1, 1 over the interval -1, 5. And this is just helping you set up your sentence, especially when you're answering those any question where you need to show your communication. So this is how you get those communication marks. And we can also call this the extreme or max or absolute maximum. And the lowest point here, this one it actually is one of our critical points. It's this point here, and it is 1, -4. So we would expect here that the derivative at x is equal to 1. So f prime of x, f prime of 1 is 0. And so this is our lowest point here, 1, -4. And so we say this is called the, again, extreme or absolute minimum at, and you have two options here. You can also do at x is equal to 1, or because it's good to know what the minimum is, the point is actually more helpful because it tells us the x value and it also tells us what that minimum value is. And then again, over the interval, -1 and 5. And this I'm just getting from here. And so you want to include exactly as is written there because 1 and 5 are included in our, or -1 and 5 are included in our interval. And that's important because here we just saw that it ended up being one of our maximums or one of our extreme values. Now, if this wasn't in the interval, you would have to consider a point much closer to see, because clearly a point very close to -1 would be even higher than this point. So that would be our maximum still there. And your function would still be, you would be given an interval there, and you would just have to interpret it based on that interval. Now, just giving definitions there, we have that an extreme or absolute maximum value occurs at a peak where the slope of the tangent is 0, so f prime of x is equal to 0, or at an endpoint of the interval a and b. And see, in both of these, it is an inclusive interval, so we can include our intervals. It would be much harder to solve it for an interval a, b, again, exactly as we are seeing here. If -1 wasn't in our interval, it wasn't inclusive, so we would have to find what value we could have for a maximum, but again, it wouldn't be an exact value because our exact value would be -1, which isn't in our interval. So you will often see closed or inclusive intervals here. And the extreme or absolute minimum is occurs at a valley. So that's when we go down like that. We have a curve that opens upward, and the slope of the tangent is also equal to 0 here. So f prime of x is equal to 0, and or at an endpoint as well. So for example, if we had that this function went something like this and ended here, then that would actually be our minimum. So we would have the extreme maximum and minimum at the endpoints and not at the critical points. And this is now a refresher. We've already seen this at the end of Unit 2 and used it implicitly in optimization problems, but this is our algorithm to determine extreme values. So if a function f of x has a derivative at each point on a closed interval, so closed interval here, so x is between a and b inclusive, then we calculate f of x uh, and this is, again, we want to see what those output values are to determine which is the maximum or minimum. So we calculate it at the points where f prime of x is equal to 0, so our critical points. And we also evaluate at the endpoints x is equal to a and x is equal to b. And we conclude that the absolute maximum value is the largest of these values, and the absolute minimum value is the smallest of these values. So now let's try with an example. Here we have a a polynomial function with a degree of 4. And so now we're seeing that this algorithm as a general algorithm, so not necessarily in an application problem. So for this function and the closed interval of -2 and 2 inclusive, so we first, based on our algorithm, we want to find f prime of x, so the derivative function. And I'm just applying derivative rules here, so I get 4x cubed plus 12x squared from here, and -4x, and then -12, and the 9 just is a constant, so the derivative is 0. So now we want to find values of x is equal to c. And the reason we write x is equal to c because now we're specifying an exact point where f prime of c is equal to 0. So here we're seeing a method of factoring, and this is factoring by grouping. And so because I have 4 terms, I pretty much was seeing if there's anything in common that I can factor out. And so between these two terms, and it's always good to order them in terms of degree so you can factor out the highest degree of x from each 2 terms. So here I had x squared in both of these, so I factor it out. And I also have a 4 in common, so I factor 4x squared, and I got x plus 3. In the next 2 terms, I see I can factor out a -4. And I actually end up with x plus 3 here as well. So by grouping, this is equal to 4x squared minus 4 times x plus 3. And this is just factoring out x plus 3 out of both of these. And now, by difference of squares for this portion here, because we have square root of 4x squared is 2x, and the square root of 4 is 2. So then we do have a difference of squares, and we can factor it out, and we have 2x minus 2, 2x plus 2, and then the x plus 3 remains. So now we want to find those values where f prime of x is equal to 0. So then in this case, we know that x is 1. In this case, it has to be -1. And in this term, it has to be -3. And now we just find what those output values are just from our original function f of x. Now, although all these 3 values are the critical points, remember our interval was -2 and 2. And so that's why we don't actually consider this, so not in our interval. So we only find the output values of f of 1 and f -1 for our critical points. So f of 1 is just 0, and f of -1 is 16. And we also have to consider the endpoints here as well. So f of -2 is also, oh, this one is 9. Oh, 9. And then f of 2 is 25. And so from here, we can see that yes, the critical point of x is equal to 1 gave us the minimum. This is the smallest of these four values. But the greatest value here is 25, which isn't a critical point. It's our endpoint. And now let's look at the graph of this and how this is shown. So consider here from this graph, which one is the maximum and minimum. So here we see we have -2, -1, 1, and 2. So our two endpoints and our two critical points here. And we can clearly see that change of direction here from increasing to decreasing and then again to increasing. And so our minimum is this value here. So f of 1. And our maximum is f of 2, which is the endpoint here. Now, had we a bigger interval, so perhaps we had -4, 2, then we would see that this curve would continue, and somewhere at where we have 3 here, this would be our minimum point there, and we would have another turning point, maybe not the best drawn, but okay, something like that. We would have a turning point there, and that would be our minimum value for the interval -4 and 2. But again, because -3 is not in our -3 is not in our interval, we don't consider it. Now, uh, just to practice yourself, try for this function as well on the interval -1 and 5 inclusive. Check that the maximum is 31 and the minimum is -21. So again, find the derivative function, calculate the points where the derivative is equal to 0, check your endpoints, and confirm that you get these values, and also confirm which x values give you these. And now we're going to do one more example here. So, technicians working for the Ministry of Natural Resources have found that the amount of a pollutant in a certain river can be represented by P of T. And T is in the closed interval 0 and 1, and T is the time in years since a cleanup campaign started. So we want to see how much pollution is left after we've been cleaning up for some time, and time is in years. So if January 1st is day 1, what day was the pollution at its lowest level? So because we are considering 0 and 1, that's actually just 1 year. So that's why it was given to you in January 1st, because you're just considering in that year, what day was the pollution at its lowest level. And so according to the algorithm, first we want to find the derivative function. So from here, we are applying the sum rule first. So this would give us 2t. And this part is the quotient rule. And so we would get -162 over 162t plus 1 squared. Now, finding the values where p prime of t is equal to 0, but again, for a specific value of c, so we are just finding this equal to -2 by just rearranging. And so solving this, we would get that we would get the square root here, or the square value here. So 162t plus 1 squared is equal to 81. Now we have two cases to consider here, because when we take the square root, we have plus or minus 9. So considering first when it's equal to 9 and then -9. So when it's equal to 9, then t is 8 over 162, which is 0.04939. But when we're considering -9, then t is a negative value. So it's not included in our interval, and we're not going backwards in time. We want to know the time after the campaign started. So we only consider this t value here. And so at that t value, we have that the polluted level is equal to 0.2098. So we have the output for our critical point, but we also now need to check and evaluate P of t at the endpoints. And especially because we have closed intervals, we really need to be checking those endpoints. And this occurs when t is equal to 0, so when the campaign is just starting, and t is equal to 1, so after a year has passed. So at t equals 0, we have that the pollutants is just 1. We haven't done any cleanup, and that actually makes sense, right? All the pollutants are still there. But after 1 year, if we evaluate this, we see that we get 2.0061. And so we can conclude that the pollution. There was the pollution was at its lowest when T is equal to 8 over 162. And also consider when was the population at its highest level and the pollution at its highest level and what was the pollution, I'll fix this for you, at this time. And one interpretation of this could be that although they are cleaning up, still people, or there's another big pollutant that enters the area, and so the pollution is after 1 year is actually greater than when they started. So that would be our highest level of pollution, and it occurs after 1 year. Okay, now we're asked to state why the algorithm cannot be used to determine the maximum or minimum values of y equals 5x over x minus 1 over the interval x in -1 and 2 inclusive, so this closed interval. And I hope you can see right away that we have that x minus 1 there. So we do have that value in our interval, and so our function is not defined for x is equal to 1. Now, consider this as 5x and then x minus 1 to the power of -1, and we're going to find the product rule. So our derivative is equal to -1 over x minus 1 squared. So now we see that the derivative also is not defined for x is equal to 1. And so the algorithm does not give us enough information to determine if we have a maximum or minimum value. Now, let's make connections from that to the graph of the function. So the graph is shown here, and we can see that at x is equal to 1, we have an asymptote, so our function here is going towards infinity, and this way it's going to negative infinity. And so we don't actually have a maximum or minimum value because it just keeps increasing here, and it keeps decreasing here. And so that would also be our interpretation. Because we have an asymptote, then there is no extrema on this interval because it's not defined. Now, if you had been given, for example, another interval, let's say like 1.5 and 3 inclusive, then you could find that the maximum would be at 1.5 and the minimum is at 3. So that's why you have to really consider the interval for any given function, because sometimes you're not going to have any extrema on that interval, but on other intervals of the same function, you will have extrema and you'll be able to solve it. Now, let's look at our last problem for this lesson. So here, and you will see a lot of these problems for this unit as well. So here we're given the graph f prime of x. So this is now the derivative function graphed, and we're asked to graph f of x. So here, the curve f prime of x intersects the x-axis at 2 points. So it has two roots there, and it is at somewhere between 0 and -1, and here it's between 2 and 3. And we've defined those here as x1 and x2. And because here so at these 2 points we have f prime of x is equal to 0, then we have two critical points or two turning points here. And additionally, here we have in these two intervals, we have f prime of x is greater than 0. So we have increasing intervals. And so it's for here and here. And then for this interval here, we have f prime of x is less than 0. So we have a decreasing function here for this part of the interval. And that's exactly what I've written for you here. So between these intervals, we have that the function is increasing, and in this portion, we have that the function is decreasing. And again, for x is greater than x2, we have an increasing function again. So one possible graph of f of x is shown here. So I plotted my 2 points here. I have a decreasing function on this interval, and here we have increasing, and as well here we have increasing. And I'll show you one more possibility. So you could also have something like this. So turning point there, and then go down, and then over here, and then go back up, increasing. And I hope you can see that there's just based on that information, you can draw pretty much an unlimited amount of functions that will satisfy these conditions. So you pick any that you want to draw. So as long as you're following the critical points as well as the increasing and decreasing parts of the derivative function, then both of these curves are satisfying my derivative function curve. And that is the end of our lesson. You do have a similar question in your practice problems, so make sure you're getting a lot of practice with now general form of critical points and using critical points for any polynomial or different types of functions. And if you have any questions, please don't hesitate to reach out, and I will see you all next class.